Hello, this is part 3 of my video, and this is an example of using expectation algebra to calculate a two-variable expectation. So what I've done here as an example is used two sort of dice games in effect. The first one is for the x variable is going to be the score from a six-sided dice. We're going to call it x, and the y variable is going to be a four-sided spinner, and these are intentionally biased so that we can see how the probabilities work, and the fact that they don't have to be equal or regular probabilities for this approach to work. So if we look at our x score first, our six-sided dice, we've got these outcomes in terms of values. We've got a 0.1 probability of getting a 1, a 0.2 probability of getting a 2, 0.1 probability of getting a 3, and we could carry on through to the end. And we know that if we multiply each of these together and then sum them, we would get our expected value or expectation, our expected score. And for the six-sided biased dice, we would expect that to be a 3.7 with the score. Then I've got a four-sided spinner with a probability of 0.2 of scoring 1, 0.3 of scoring 2, 0.1 of scoring 3, and 0.4 of scoring 4. And again, if we multiplied these together like that, we would get an expected score on the four-sided spinner of 2.7. So those two are happening separately. And then we're going to look now at what's the probability of certain outcomes if we combine these into a single score. So having a look here in this first place in our space, so effectively our probability space, here we've got a score of 2 because the x score is 1 and the y score is 1, and the probability of that happening, well, we've got a 0.2 probability of scoring 1 on the y spinner, and we've got a 0.1 probability here of scoring 1 on the x dice. And we can follow that through. So if we went down this first column, here's the scoring 3, so we've got 2 on the spinner and 1 on the dice, and the probability of getting a 2 on the spinner is 0.3, and the probability of 0.1 on the dice, the probability of getting 1 on the dice is 0.1. And so here we have our score, that's our value, and our weighting is our two probabilities multiplied together. So here's our score of 3, and our weighting here is the combined probability is 0.3 times 0.1. And we can go through here, so we've got 6 times 4, we've got 24 outcomes. Now let's have a look at how this table fits together. What we see here is if we look down the first column, all of these numbers in the first column have a 0.1. And if we were to write that algebraically, then we've got that probability 0.1 times the sum of the x and y scores times the probability of y. And if we went the other way and we went along the first row, we'd see every number in the first row has got a multiple probability of 0.2. That 0.2 is the probability of getting 1 on the four-sided spinner, and therefore an algebraic expression for that would be 0.2 times the sum of x and y times the probability of x. And if we went through and did all of those calculations for each of those 24 and then added them up, we'd get a value of 6.4, which we would expect to be the sum of the expected value of x and the expected value of y from what we did in the last video. But let's have a little bit more of a look at why that happens. Now, if we took, let's take this top corner calculation here. So our overall score was 2 is made up of the 1 from the six-sided dice and a score of 1 on the spinner. There's our 2, and there's our 2 probabilities. Now we could actually break that number up into 2 separate calculations. We can have 1 for the one there for the score on the six-sided dice, and we could have a score of 1 for the score on the four-sided spinner, and we add those together, we get 2. We could do that and split up each one of the scores into, so going down this column, each of these has got a score of 1 on the six-sided dice, but it's got a different number. Here's 2 on the spinner, here's 3 on the spinner, and here's 4 on the spinner. Now, if we look down this column as well, we see that, as we saw before, that we've got 0.1. Just look at these yellow numbers first. That each one of them has got a 0.1 on the end as the multiple, because that's the probability of getting a 1 on the six-sided dice. But if we look at the first 2 numbers multiplied together, here we've got 1 times 0.2, and here we've got 2 times 0.3. Here's 3 times 0.1 and 4 times 0.4. And if we look to our column on the left-hand side here, we can see these are our contributions to the expected score on the spinner. So that will be our expected value of y, and we can therefore see that what we've got here in the first column in yellow, if we add them all up, is the expected value of y times 0.1, which is the probability of the spinner, the x, being a 1, being scored at 1. And if we go through the same thing, if we look at the second column, we'll see we've got the same 0.1 and 1 times 0.2, 2 times 0.3, etc., as we saw in the last column. And if we look at the next column, we'll see exactly the same on the yellows. So each of these has got exactly the same first 2 multiples, hasn't it? And what varies in each column is the third number. So let's have a look at the third number. In the first column, it's the 0.1 probability. In the second column, it's the 0.2. In the third column, it's the 0.1, 0.3, 0.2, 0.3. If we look, therefore, at the bottom of each column, the sum of this is going to be, each one is the expected value of y, and here's the 0.1, the 0.2, the 0.1, the 0.2, the 0.3, and the 0.1, which are all these probabilities here, the probabilities of those scores on the six-sided dice. And if we add up those probabilities, of course, they're all going to come to 1. So therefore, if we just added up all the yellow numbers in this table, the 24 yellow numbers, if we calculate them out and added them up, we would get the expected value of y, i.e., which is 2.7. Okay. Now, if we go in the, rather than going down the columns, which we just looked at, let's have a look at these orange numbers here. So if we start going across the top row, we've got each one of these has got a 0.2 in the middle, and that 0.2 is the probability of scoring 1, isn't it, on the spinner. And then the first number here in each of these columns in this row is 1, 2, 3. These are the scores. These are the scores on the dice, aren't they? And if we combine that 1 in the first column here with the 0.1, that's the score. That's the probability of scoring 1, isn't it? And here, these 2 numbers, that's 0.2, which is a probability of scoring 2. And then we've got 0.1 times 3 is the probability of scoring 3. And for each one of these, we can see that these are the contributions. 1 times 0.1 is the contribution to the expected value of x. 2 times 0.2 is contribution to the expected value of x. And therefore, if we have a look at this, each of those multiplied together, where I've got the little red, sorry, green line between them, would give us the expected value of x, wouldn't it? And then each of them in the first row is multiplied by 0.2. In the second row, it's multiplied by 0.3. third row 0.1, and finally the last one's 0.4. And of course, if we add up those probabilities, they all add up to 1. Therefore, if we summed up the orange numbers here in this column here, we would have E of x, wouldn't we? Expected value of x, which I think was 3.7, wasn't it, we calculated. And therefore we can see that if we sum all the yellow numbers going down into the column at the bottom here, into this row of values at the bottom, we get EY. We can easily see that's EY, which is 2.7. And if we sum the orange numbers across to the final column here, we would see that they would sum to e to the x, which would be 3.7. So hopefully you can see that using this approach we can see why, by thinking of this as a table and splitting it up and looking at those probabilities, we can see why e to the x plus y will always equal e to the x plus e to the y. So I hope that's of use.